Okay, hey, let's get back into it and do the last few. Last few meaning second half, actually, but whatever. Let's start here. I think I talked about this one in one class. I don't think I talked about it in both, though. So looking at this, you've got this cubic, x cubed minus 1, over this quadratic, x squared minus 1. And we know that the denominator factors to x plus 1, x minus 1. But what you might not know is that the numerator does also factor. We had a formula for a difference of cubes. And that formula says, well, let me start with the difference of squares just to kind of jog your memory. But a squared minus b squared is how we would write out the general rule. And we said that it factors down to the square root of whatever this first thing is, so a, square root of the second thing, so b, and then it's just ab with alternating signs. It's plus minus. Okay, so differences of cubes are similar. If you had an a cubed minus a b cubed, well, the pattern is similar, I guess, but it's cube roots, so it's the cube root of a cubed and it's the cube root of b cubed, and that's a binomial. But then you get a trinomial where the first term is the cube root here, a, but squared. And then it's the cube root of this term, so b, but squared. And then it's the cube root times the cube root, so a times b in the middle. Then the sign pattern, the pattern of the signs. If you're factoring a difference, then you get the same sign. Notice, I'll just jump ahead and say that sums of cubes are also factorable. And they have the same pattern in the exponents. It's a to the 1, b to the 1, then it's a squared, then it's a to the 1 times b to the 1, then it's b squared. So it's the same pattern. But the signs follow a different pattern because this time you're factoring a sum, so you want the same sign. Notice that in the first position it's always the same. So if you're factoring a difference, it's a difference. If you're factoring a sum, it's a sum. Then you want the opposite sign. So we're factoring a difference, so this should be a sum. Here we're factoring a sum, so this should be a difference. And then the last sign is always positive. Always positive. So there's a way to remember the sign pattern. If we're always doing the same sign, and then the opposite sign, and then we're always positive, then you kind of just remember the word soap. Soap. And that's telling you that once you've factored this thing out, the signs would follow a pattern where the first sign is the same, the second sign is the opposite, and the third sign is just always a plus. So that's it. That's good to know. I'm going to huck this in the bin. The mouse is being weird and I don't like it. I'll take these and just get them out of here because we need room. Store those right there for a moment. No, up there for a moment. Okay, so that means I can factor my numerator. And I will land on an x and a 1 and an x squared and an x times 1 and a 1 squared. And then following my sign pattern, it should be the same sign, opposite sign, and always a plus. So there. That means we can now see that this factor of x minus 1 cancels out on us and generates a hole in our graph. And that means our simplified form is x squared plus x plus 1 all over x plus 1. And notice I'm not checking if this quadratic is factorable because I know that it isn't. Every single time you factor a difference of cubes, the quadratic bit that you get over here, it'll never be factorable. So you don't even have to check. So what am I supposed to say now? I'm supposed to say that x cannot be can't be positive 1. Okay, so there you go. So that's your factored form. So then from here we make all of our decisions, and the decisions we have to make are about all of these things, remember? So we've got the factored form. We need all of our asymptotes now and all of our intercepts and all that good stuff. So for factored form, I'm just going to say check because there it is up there. For vertical asymptotes, the factor that didn't cancel is our vertical asymptote. It's x equals -1. The factor that did cancel, the x minus 1, generates a hole whose x coordinate is 1. And real quick, if you did not know how to factor, then here's what you could do. Looking at the denominator, you know that your zeros are -1 and 1. You could, of course, take these and just plug them into the numerator to see if they make 0. You can test for zeros without knowing how to factor. So plugging in -1 gives -1 cubed minus 1, which is -1 minus 1, which is -2. So you can see that -1 is not a 0 of the top and bottom, so it's not going to cancel, and it's going to make an asymptote instead of a whole. Then you can test the +1, and suddenly 1 cubed take away 1 is 1 minus 1, which is 0. So you can see that that 0 of the denominator is also a 0 of the numerator. So even if you did not know how to factor, you could still determine that at x equals 1 there's a whole instead of an asymptote. Okay, so there's still kind of a workaround if you didn't know how to factor. Horizontal asymptotes, we know that we don't have one, because we know that our numerator has the greater degree. For slant asymptotes, well, I guess it's time to do some polynomial long division. So let's do that. I guess over here, there should be enough room. By the way, I guess technically you could do the polynomial long division with the original form of the function, but there's no reason to, because we know that this red form of our function is completely equivalent to the original form, except for when x equals 1. And so I may as well use the simpler version. So let's just divide x plus 1 into x squared plus x plus 1. And this hopefully will feel a little bit simpler. But as I divide in, x squared divided by x gives me x. So I know that's my first quotient. And I'll distribute that through to get x squared plus x. Then I'll subtract. These cancel. The x's also cancel, so there's no x term. So by the time I drop down the 1, that 1 already has degree less than my divisor, so I now know that that 1 is pure remainder. This guy here is pure quotient, and this guy's my divisor. And again, the only part I care about when I'm trying to write the equation of the slant asymptote is that quotient. So our slant asymptote is just y equals x. We did talk about how the remainder comes in handy, and I'll circle back to that later, I'm sure. But let's do, I don't know, I guess we better finish off the whole. We only know the x coordinate of the whole to be 1, and we said to find the y coordinate, you have to take x and plug it back in, but you don't plug it into the original function, because the original function still contains this x minus 1 factor, which will cause division by 0, which will make us undefined. But to find the y value, you can plug into the simplified version over here, the one where the x minus 1 has been canceled out. So plugging in 1 is going to give me 1 plus 1 plus 1 all over 1 plus 1. So that's looking like 3/2 to me. So that's the coordinate of our whole. Then the x-intercept. The x-intercept would be when the numerator equals 0. And I just told you not too long ago that this quadratic that you get after factoring a difference of cubes, I just told you it's not factorable. If this thing was factorable and we got x plus 3, x minus 4 or something, then the zeros would be our x-intercepts, right? Would get -3 and would get +4. Well, do you know why some quadratics aren't factorable? Well, they're not factorable because their solutions are not nice, clean values. They're irrational numbers instead. So any quadratic that isn't factorable, I shouldn't say that. That wasn't quite right. Or was it? I think it was. Of course it was. As long as your solutions are rational, like fractions, then you can be factored. But if you can't be factored, it's because you're irrational, meaning you can't be expressed as a fraction, meaning it's some number that involves a radical. Okay? Think about it. The quadratic formula says -b plus or minus the square root of b squared minus 4ac. All over 2a, which I hope you remember from Algebra 2. But basically what I'm saying is the solutions here come from this formula, and if I end up trying to take the square root of a number like 7 or 23 or some other garbage value, then it's not going to be a nice clean integer value. It's going to be irrational, and that's why you can't factor. Anyway, long story short, the fact that this guy isn't factorable tells me that my x-intercepts are irrational numbers, which technically could still be zeros. So technically, I should be testing this by plugging into the quadratic formula, but you know what, I'm not gonna, because I got a sneaking suspicion that my graph just comes up and goes back down, and then it comes down and goes back up. And I got a sneaking suspicion that instead of just ugly irrational values, I'm just getting imaginary values, or technically I should say complex values. And that would imply that there are no x-intercepts. I feel pretty safe saying that without actually testing this. We'll find out in a minute. But for a y-intercept, we should have one. We plug in 0 and see what we get. And plugging in 0 gives me 1 over 1, so 1. So I know that 0, 1 is a y-intercept. And I still feel safe assuming that there's no x-intercept. So let me get this rough sketch out of here, and we'll try to make a real sketch. Okay, so our real sketch then would include our vertical asymptote, which we decided is at -1. I wanted that to be red, but blue will do. And then x, remember x, y equals x just is a y equals 1x plus 0. So you know you've got a y-intercept at 0 and a slope of 1. So rise 1, run 1, rise 1, run 1, run. And then you can sketch that asymptote in pretty easily. Okay, so what do we know? We know that we have that y-intercept at 0, 1. So that does seem to tell me that my graph would lie completely above this slant asymptote. Problem is we have that one wrinkle that says that sometimes our graphs do come down and cross their slant asymptotes or their end behavior asymptotes, and then maybe it approaches from underneath. Luckily for me, I know we don't do that, and hopefully you remember from class that we don't, because if you re-express f of x in that quotient plus remainder over divisor form, then that would be x plus 1 over x plus 1. And we said that one quick way to test if the function crosses its end behavior asymptote was to just look at this piece on the end, the remainder over divisor, because if this term is ever equal to 0, then the solution that makes it equal 0 is the point where you cross your end behavior asymptote. But I know that this never equals 0, because the zeros would be the zeros of the numerator, and the numerator is just 1. There's no x there, it's just a constant function. So I know that this term never equals 0, and that allows me to rest assured that we never cross the slant asymptote, which means that this kind of scary situation of having a graph that actually crosses its end behavior asymptote and comes up from below, that can't happen. And that also does guarantee that I do not have an x-intercept. So delete that. Oh, rats. Delete that. Got it. Oh, rats. Delete that and only that. Okay, got almost all of it. Okay, okay, I'm feeling good about this now. I'm feeling totally confident that in this little window I'm coming down, hitting a y-intercept, then I think probably after there I'd achieve some minimum and I'd come back up. And now technically my next branch could be above again. That is a thing that happens. So technically, maybe there's an x-intercept over here, but we could convince ourselves otherwise by just running a test point. So you pick any number less than -2 and you just test it to see if the value that you get is greater than the slant asymptote or less than the slant asymptote. So I'm going to test a value of, I don't know, -3 seems like it's in a good place. So at x equals -3, first of all, what's the slant asymptote? Well, the slant asymptote's equation is easy. It's just y equals x. So you know that at -3, the slant asymptote has a y value of -3. So we're testing against that cutoff point. Now the function at -3, when we plug in, I'm going to plug into, I guess, my simplified form, right? But -3 squared would be +9, take away 3, plus 1 over -3 plus 1. That's 6 plus 1 is 7 over -2. That's -3.5, and that means we are ever so slightly less than the -3. So we've got a point here. which does guarantee that I'm entirely below. I come up and I achieve some max, then I come flying back down. And I would like to say I've done a wonderful job here, but I forgot something. Because we had a hole. Don't forget we had a hole. I forgot to plot that. So before this confuses anybody, I was just marking that spot. That wasn't our hole. Our hole is actually on the graph, and it's at 1, 3/2. So if I go to 1, 3.5, there should be a hole right here. And we said we're going to make them nice and big so that I can see them. And I'll white out the middle. But there's a nice big honking hole that you can see. Nobody's going to miss that. And there's your graph. Everything we need is here. We can see that the x-axis does run right through the middle, and there are no real x-intercepts. There are complex or imaginary intercepts, but those don't count. Okay, so that's 8 for you. Let's go do 9. Let's go do 9. And that took 16 minutes to do one problem. Yikes. It won't take you 16 minutes on the test because you'll fly through it and you don't have to explain it to a whole population of kids that may or may not understand. You'll be able to go a lot faster than I do. All right, look in here. I know my first step is factor. So out pops an x, and I get x and 2x minus 3. In the denominator, I just have an x plus 1. So I know a lot of stuff here already. This was easy to factor. No cubics or nothing like that. So my factored form, check, I'm already done. Oh, actually, hold on one second. Okay, I'm back. So we factored, and based on our factored form, we now have a bunch of information. We know that the 0 of the denominator, since it doesn't cancel, represents a vertical asymptote. We know that we don't have a horizontal asymptote because we have another problem where the numerator has the greater degree. And that implies that we are going to have a slant asymptote, which we can find by doing long division. So let's do long division. We're going to take our divisor, the x plus 1, and we're going to divide it into our numerator, which is the, you don't want to use the factored form, of course. You want the expanded form. So go back to the original expression and grab the x, the 2x squared minus 3x. And then start doing your division. Technically, I like to see these placeholders. I want something to fill in the constant slot. I think it doesn't matter when it's a 0 at the end, but I'm still going to do it anyway because it's just a good idea. But all right, so when I'm doing this division, I'll just take the 2x squared, the first term of my dividend, and I'll divide it by the first term of my divisor, and I get 2x. So that means I need a 2x in the x column, and I'll distribute that through, getting 2x squared, which of course is exactly what I'm always supposed to get. I'm supposed to get the same thing. Then it distributes onto the 1, and I get 2x. And now I subtract. And when I subtract, these cancel, like they should. And over here I get negative 5x. And then I guess I drop a 0, but no, it's definitely not important. But now I do the whole process again, and negative 5x divided by x would give me negative 5. And I guess at this moment I could stop and just give the answer of y equals 2x minus 5. But I don't know. There's a couple reasons why I shouldn't. One of those reasons is the remainder is kind of important. If you get a remainder of 0, then that actually means that the x plus 1 is a clean divisor of the numerator, and it means you probably factored wrong because it means the x plus 1 should have canceled. If you get a remainder of 0, then that denominator should have canceled out. And then we wouldn't have a slant asymptote. It would have a line with a hole in it, and it would be different, and you better just be aware of that. But we're going to find that that doesn't happen anyway, because when I distribute the negative 5 through, I'll get negative 5x minus 5, and I do see that I've got a remainder of positive 5. And in the last problem, we talked about the remainder. We said that the remainder, come on, take me back. We said the remainder indicates whether you cross your end behavior asymptote or not. And we saw one. We saw a remainder over divisor, where the remainder was a constant, which meant it could never equal 0, which meant that the whole function didn't cross its end behavior asymptote. So we actually know that this is another. This is another function whose remainder is a constant, and therefore it can never equal 0, and therefore the function cannot cross its end behavior asymptote. That's good information to have. So we know that that's already happening. So our slant asymptote is this. We don't cross it. Exclamation point. And again, I actually had questions ready here for that, but does the function cross the same behavior asymptote? You're going to say no. No. If so, where? You're going to say not applicable. If I asked you to justify why we don't cross, you'd say remainder does not ever equal 0. That's it. All right. So where was I? We were going to talk about holes. We don't have any. We're going to talk about x-intercepts. Well, the x-intercepts are the zeros of the numerator. And so I can see I've got a 0 at 0 from the x. And I've also got a 0 of positive 3/2. Oops, I'm doing this wrong. I don't like you to give me the x-intercepts as x values. I like you to give me the x-intercepts as ordered pairs. So let's actually strike that. And we'll instead say that one of our intercepts is the ordered pair, 0, 0, and the other is the ordered pair, positive 3/2, 0. And if your x-intercept is 0, 0, then obviously your y-intercept is also 0, 0. But again, the y-intercepts come from just what you get when you let the function, or when you evaluate the function at 0. So plugging in 0, you can see gives 0 over 1, which is 0. So the y-intercept is 0 for that reason, because I plugged in 0 for x. The x-intercept is 0 because 0 is one of the zeros of the numerator. So we're getting the same answer for two different reasons. All right, I think I've got all the pieces I need, so I'll plot my x-intercept. My next x-intercept is 3/2. That's 1 1/2, so that's there. My vertical asymptote is at -1, so that's here. My slant asymptote is 2x minus 5, so I got to go down to -5. And I got to use a slope of 2, so rise 2, run 1, rise 2, run 1, rise 2, run 1. And then you can just rough in your slant asymptote. Line here, line here, line here, line here, line here. So that's looking fine. I don't love this, obviously, because there's no room down here, but this is the grid they gave us. This grid, it's already marked with a scale. If there was no scale here, then maybe we could have chosen to go, I don't know, we're going by 1s. If we had gone by 2s, we could be further down. We could have a little more room here. I don't think I super care though. But just given these 2 points here, I can rest assured that we're coming down, hitting here, achieving some minimum in the middle, turning and going back up. And because we don't cross the slant asymptote, and because the degrees of our function are relatively small, I would wager lots and lots of money that our next branch is down here. But I would also say, look how far away this is from this point of intersection down here at 5. There's a gap here in the y direction of what? This is 7? So like a 6-unit gap here. So that means if this is 7, I need to go all the way down to 13 to see where my max is. So I wouldn't see this branch at all. So this scale is so bad that I don't even see it, okay? So you actually can't even show the other branch down here unless you like extend the grid way the hell down. But our graph would be like way down here actually, if we were truly going to draw it. And you know that. You do know that because this graph has a kind of odd symmetry. It's not odd symmetry, of course. But if this point here was the origin, then we have sort of odd symmetry around this point, right? And so as far over and up as I am, I need to be left and down that same distance, which pushes our second branch off the grid. I'm over-explaining this, I'm sure. But if you haven't figured it out yet, my philosophy is to over-explain rather than under-explain. So hopefully you guys understand why I'm not showing you the other branch. It's because it's way the hell off our grid. And that shouldn't be an issue on tomorrow's quiz. I'll give you grids on which the graph fits. Okay? That's 2 questions down in 24 minutes. Let's move on. Bing. Here's 10. So 10 is quadratic over quadratic. This could potentially be interesting. Let's factor first. So my numerator is an x minus 2 and an x plus 1. in my denominator is an x minus 3 and an x plus 2. So I don't have common factors, so that means I will have two x-intercepts, I'll have two vertical asymptotes, and it should be fine. I don't really see anything terribly weird about this. So as far as factored form, we're done. We did it. As far as vertical asymptotes, both of the zeros of the denominator turn out to be vertical asymptotes. So that's one at x equals -2 and another at x equals +3. Horizontal asymptote is at y equals 1. Think for a second. Do you remember why? I hope you did. The answer is, of course, because we have equal degrees. And that means the rule kicks in where we look at our leading coefficients. So our horizontal asymptote is at y equals 1 over 1, which is 1. Okay? For slant asymptote, we don't have one, because you only have a slant asymptote when the degree of the numerator is greater, and only when it's greater by exactly 1. For holes, we don't have any, because we don't have any factors that cancel out. For x-intercepts, we do have some, because they're the zeros of the numerator. So -1, 0 is going to be an intercept, and +2, 0 is an intercept. And for y-intercepts, this is when you substitute in 0, and f of 0 seems to be giving me 0 minus 0 minus 2 over 0 minus 0 minus 6, which is +1/3. So 0, 1/3 is our y-intercept, which means I should now be able to go to town and sketch this graph kind of quickly. Why don't I just use my dotted line tool to put a vertical asymptote at -2, shrink, and one at 3, shebang, and our horizontal asymptotes at 1, bazow. So there's everything all cordoned off. My x-intercepts come in very handy as test points, so let's plot them. -1, 0 tells me that I must be below this asymptote. 2, 0 tells me that I'm still below this asymptote. So could I come up, cross the asymptote, and then come back down through the asymptote again? I don't know. Maybe I could. So how do you test if you pass through your end behavior asymptote? Well, one question ago, I said that if the remainder was equal to 0, then you'll pass through your end behavior asymptote. 2 questions ago, I said the same thing, that if the remainder equaled 0, we'd pass through our end behavior asymptote. The only problem with that strategy is we never bothered to find our remainder here by doing polynomial long division, because we knew that we didn't have a slant asymptote, so we don't have a remainder. So we probably better fall back on method 1 for determining if you cross your end behavior asymptote, which was grabbing the entire original function, the x squared minus x minus 2 all over x squared minus x minus 6, and setting it equal to the equation of our end behavior asymptote, which in this case is y equals 1, which means I just have to set this thing equal to 1, and then just try to solve this. And if I get a real solution, then that solution, or solutions, it could be plural, then those solutions would represent points where I cross the end behavior asymptote. But if this thing turns out to have no solutions, then you know that you do not cross. So how do I solve this? The easiest way to think about it is that you're just going to cross multiply. The slightly more mathematically rigorous way to think about it, I guess, is that you're multiplying through by the LCD of all of the fractions. But the LCD would just be the one denominator that we have, the x squared minus x minus 6. And you're multiplying everybody by that. So it distributes here, and it just gets canceled out and gives you back the numerator, x squared minus x minus 2. Then it distributes onto the 1, and it just equals itself, x squared minus x minus 6. So what often happens is your term with the greatest power cancels out. If I subtracted x squared from both sides, it'd cancel out. Then it turns out here that if I add x to both sides, then they cancel out too, which leaves me with the very interesting equation of -2 equals -6, which of course it doesn't equal that, which implies that we have no solution. And if we have no solution, then we have no points of intersection. So that means I now feel the utmost confidence saying that this entire branch of my function must come through, hit right here, come over, ooh, that was that got bendy. I must come up, 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 and hit right here, achieve some max in the middle, come back down and go back down. All the while, I'm staying below this asymptote. Now the other two branches are a bit of a crapshoot. I would wager every single penny I had that they're gonna fit here and here, because I know that the only time that you get a branch on the same side as the other branch really requires powers higher than 2. And so this guy should still be relatively simple. And by simple, I just mean that if you get an uppy branch, then the next branch is a downy branch, and then the next branch is an uppy, and it's going to alternate like that. The only time you don't have that happen is with higher powers. So even though I would wager every single penny I had, I'm still going to run test points because I must, just in case. So let's come up with an x value that's to the left of this asymptote. There's a 4 right there, so let's just use the 4. And then let's calculate the y value. And remember, we're not testing against 0. There's a lot of confusion around this in my 3rd period class. And my 2nd period class, I'm not sure we talked about this. You guys didn't really ask about it. But I'm not testing for like positivity, negativity. I'm testing for, are you bigger than 1 or less than 1? And there is obviously a difference. Because if I get a half doesn't mean I'm up here and I'm above. A half means I'm here. A half would be below 1 and I would live down here, right? So just be careful. Make sure you have your cutoff points in mind when you run these tests. Okay, blah, blah, blah. -4 yields what? I'm going to test the factored form. You could test the other form if you wanted to. I'll do both just for the sake of it. If I was testing here, the -4 squared would be 16, minus -4 is +4, take away 2. In the denominator, I'd get 16 plus 4, take away 6. That's 20, take away 2 is 18. And it's 20, take away 6 is 14. Right? Yeah. And so that's a number greater than 1. I honestly don't care how big it is, really, as long as I know that it's greater than 1. But I would say it's greater than 1, but it's less than 2, so it's definitely somewhere in the middle. And all that really means is every penny I own is safe, because I said would be up here, and we are. Whoops-a-daisy. Hey, let's test the other side. So what do we get? 9/7. All right, let's test the other side. We could test +4. I'm going to test 5 just to get a different looking value. And this time I'll test the factored form. But plugging in 5 minus 2 is 3. 5 plus 1 is 6. 5 minus 3 is 2. 5 plus 2 is 7. So I'm looking at 8. Ah, rats. Wait, damn it. I was trying to get a different number. I should have used the 4. Yeah, that makes sense. Just to explain this to anyone who cares, -4 is 2 units away from the asymptote, and 5 is 2 units away from the asymptote. So I'm getting the same y value because we do have a kind of even symmetry over, this mirror line. And so by picking one point that was the same distance away on both sides, of course I got the same y value. I was trying to actually avoid that happening, but I screwed it up. I don't think anyone cares though, but thinking about this symmetry is probably something you kids should do as honors pre-calculus. So 18/14 is giving me the exact same 9/7 that I had before, because of course it is. Because symmetry. Because this point goes right here. And then I can graph the other half. Alright. That's what that one should look like. And again, nothing terribly interesting here. There's no holes, and we don't cross the horizontal asymptote. So is this very representative of what you'll see on your quiz? No, because you will see holes, and you will see points of intersection with end behavior asymptotes. So just make sure that you're thinking about those things, even though they're not necessarily represented in all the homework problems. But be thinking about holes and be thinking about points of intersection with the slant asymptote, because we did see a hole in 8 in this very video. Did we see a point of intersection with our asymptote somewhere? Number 3 had it, right? Yeah, in number 3 we crossed at 0, which wasn't super exciting. But in number 4 we crossed at 6. So those are sort of the things that sort of separate on level from honors. Those points of intersection and those holes and stuff kind of elevate us to the honors level. So, you know, be forewarned that they'll be there for sure. 9 we did, 10 we did. It sounds like we're on 11. All right. So for 11, you should factor your numerator, but we've got a leading coefficient. So when we factor, you'll want to multiply. But you know it's going to be 2x plus something and x plus or minus something. But our target value, the 2 times negative 4 is negative 8. So if I'm trying to get a negative 7, I'm going to be going with negative 8 and positive 1. And again, we talked about how when you do your outer product, you already have a factor of 2. So I can't get a factor of 1 unless I put a 1/2 here, which you're not allowed to do when you're factoring. We're supposed to be using integers only. So I know I'll just, instead of going after the 1, I'll go after the negative 8 because I can just put a -4 here. Cool. Now to get the 1, I can put a +1 here, and my inner product will turn out to be the 1 that I'm after. And I'm done. I'm done factoring. And I'm just using a method of kind of guess and check. I'm just kind of guessing about which terms have to go where. And then once they're all there, I check by actually foiling, by actually multiplying to see if I get the right thing. So I'm going to literally check by just multiplying. Okay, I do my firsts, that's a 2x squared, that's great. I do my outers, that's a negative 8. And then I do my inners, that's a positive 1x. And then I do my lasts, and that's a negative 4. And that's 2x squared minus 7x minus 4. Oh, that's exactly what I wanted. So I guess that is the correct factored form. Get rid of all this blue. Okay, and so that puts all of this over x plus 4, which means we are staring down the barrel of another problem that's not so terribly interesting. Because I don't have a hole. I do not have a hole. And that's fine. Maybe I still cross the slant asymptote. Maybe I do. Let's find out. But I'm factored. Yoink. So here's all the things we should consider. Factored form, blah, blah, blah. Let's say factored form, check. I did that. Vertical asymptotes, x plus 4 gives me a vertical asymptote at x equals negative 4. The numerator gives me zeros at positive 4 and negative 1/2. So those will be my x-intercepts. Negative 1/2, comma 0, and 4, comma 0. So that's it for zeros. For horizontal asymptotes, I'm not going to have one because we're back to a degree that's greater than the degree of the denominator. So I'm expecting a slant asymptote. And to find its equation, I got to do polynomial long division. So we're back to that. So I'll take my x plus 4 denominator. I'll divide it into my numerator. And again, not the factored form, the expanded form. So 2x squared minus 7x minus 4. I wonder how quickly I can go through this without losing you. This goes into 2x squared 2x times. Distribute that through. 2x squared plus 8x. And then subtract to be left with 15x. Negative 15x, of course. Drop the negative 4. Do it again. And we see x goes into that negative 15 times. At which point I'm enraged because I see now that I cannot fit. I can't fit that slant asymptote on this grid. So, oh well, I guess we'll have to fix that and work around it. But the negative 15 times x minus 4 gives me negative 15 x minus 60. So when I go to subtract, I get a remainder of positive 56. So what does that tell me again? It tells me this is my slant asymptote, this is my divisor, here's my quotient, and I am back to a quotient that is linear? No, I'm back to a quotient that's constant, which means I can't cross my slant asymptote. So that means number 11 officially has neither of the things that I just said were important. We don't have holes, and we don't cross our in-behavior asymptote. So this is another just kind of on-level precalculus problem that would not be terribly representative of your quiz. But does it cross the in-behavior asymptote? No. If so, where? Not applicable. But whatever, let's see if we can't get something going here. Our slant asymptote at least has an equation of y equals 2x minus 15. We said there aren't any holes. We found the y-intercept. We found the x-intercepts. The y-intercept, again, is what you get when you plug in 0. So that'll give you negative 4 over 4, which is 1. So 0, comma, I meant to say negative 1, of course. But I already know that this grid is no good. So let me go get a grid that is good. Be right back. Okay, I'm back, and I got a new grid, and all I had to do to make everything fit was increase the scale by a factor of 6. Negative 10 to 10 wasn't going to work. We got to go to like all the way down to negative 60 and all the way left and right, blah, blah, blah. Anyway, whatever. I'd like to think you guys would have known the basics either way. So what would I do from here if I was graphing? I would put a vertical asymptote at x equals negative 4. You knew that. I would plot a slant asymptote at y equals 2x minus 15. That's here. See how I guess we're counting by 5. So 5, 10, 15. There's the y-intercept. And we're rising and running by 2. Because we are. This is 10 right here. We're down at 15. So you can see that we've risen 20 in a span of 10. That's a slope of 2. So it's all legit. Now what? Now you just have to figure out where your graph fits. And it either fits below and then above, or it fits above and then below. So our graph is either the red stuff or the green stuff. And again, it's easy to figure out which it is by just running some test points. And we already have a test point. One of our test points is our y-intercept, which is 0, negative 1. So we're here. So that tells me that this branch for sure is up above the slant asymptote. Don't forget you also had your x-intercepts at negative 1/2, boink, and positive 4. What are we counting by here? Counting by 5s. So we're like here. But that's great. Given those 3 points, we can see this branch for sure is here. Alright, resist the temptation now to just graph the other branch. Show me at least one test point. And so if you need a value less than negative 4, then negative 5 is an obvious choice. So x and y. Let's plug in. I like to plug into the factored form usually. So negative 10 plus 1 is negative 9. Negative 5 take away 4 is also negative 9. And in the denominator, we're also getting negative 9. So those cancel, you get negative 9. Hey, what were we testing against? Is negative 9 far enough down? Doesn't look like it is, actually. Is Mr. F bad at math? Negative 5. Negative 10 plus 1 is negative 9. Negative 9. Oh, yeah, I'm bad at math. Negative 5 plus 4 is negative 1. So we're actually getting... Okay, hold on now, Mr. F. Oh, yeah. So we're getting negative 81. Okay, at which point I would say that's definitely far enough down. Although, you know, again, just for good measure, we are supposed to be testing that value, right? So negative 5 along the slant asymptote, that is pretty far down. It's clearly not 80 down, but to show the math, you'd plug into the actual equation of the slant asymptote. You'd get negative 10 take away 5, and you can see that your break point here, so to speak, is only negative 25. And negative 81 is decidedly below that. In fact, it's so low that it's not even on my grid, okay? But it's way the heck down here. So that does tell me that our graph must come screaming up, 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 along this thing, turn, and go back down. Again, we could use our odd symmetry to do this. Just kind of thinking about this cutoff point as sort of my point at which I have odd symmetry. We're over by how much? If we're over by 4, then we're going up by that much. So if I'm left and down by the same amount, and I don't want to go crazy about this, but you can shape your function by just thinking about symmetry. We know that we have odd symmetry, so we know that sort of the local maximum of this branch should be in the same relative position that this local minimum is at, relative to the point of intersection of these asymptotes, because we're exhibiting that a sort of odd symmetry. Okay? All right. Again, I'm over-explaining things. But that's what I do. What did I just do, by the way? I just killed this. crud. What have I done? Oh, I must have hit this. Oh man. There we go. This is how it was? I don't remember. I don't care. All right, that's 11. We still have 3 to go. All right, these next couple are a little bit rough. I mean, I would say a defining feature of these rational functions we've been talking about is the fact that they're fractions whose denominators can sometimes equal 0. And when those denominators equal 0 is when we get interesting stuff like vertical asymptotes or holes. And then, another defining feature is that we typically are seeing functions whose graphs are sort of hyperbolic in shape, right? Well, 12 is going to give you none of that. And neither is 13, because both of these have denominators that are x squared plus something. So imagine if you set that equal to 0 to try to find the zeros of your denominator. Your very first step would be to subtract something from both sides, giving you a negative. Then you'd try to take the square root, giving you the square root of something negative, plus or minus, by the way. This would be plus or minus imaginary unit I. So that would mean your x-intercepts are imaginary. You don't get any x-intercepts. Oh, super psych, not x-intercepts, but your discontinuities are imaginary. So your graph wouldn't have any discontinuities. This graph, I expect to have a domain of all real numbers. It's just going to be one smooth continuous graph with no breaks. And same thing for 12. Because again, if I tried to take x squared plus 5, set it equal to 0, then I'd end up with x squared equals negative 5, which means that x equals plus or minus the square root of a negative number. It would be plus or minus I times the square root of 5, which again is imaginary. So we're not going to get all the stuff we're used to getting. So okay, that's fine. I would say this is yet another problem type that separates on level from honors, is you guys have to think about, okay, well, what does the shape of the graph look like then? They don't all look the same. So here's a new shape. So what questions can I still answer? Let's find out. Do I have vertical asymptotes? We just said that we literally don't have any discontinuities, so vertical asymptotes is none, and holes is none. Our denominator has the greater degree, so our horizontal asymptote is y equals 0, and our slant asymptotes are none. Our numerator is a constant, so it never equals 0, so our x-intercepts is none, and our y-intercepts is none. All right, super great. Let's graph this bad boy. We have a horizontal asymptote at 0, and then we have literally nothing else. Did I just say we had no y-intercept? I did. All right, so what do we look like? I do not even know. Yeah, I lied when I said we had no y-intercept. I got confused. All right, that never made sense. I don't know why I said that. Your y-intercept, again, is what you get when you plug in 0. So if you plug in 0, you get 7/5. So 7/5 is only slightly greater than 1. So what do we know? Is this graph going to cross its horizontal asymptote? Well, I guess we could find out. Its horizontal asymptote is 0, though. So does this graph ever equal 0? If I multiply through by this denominator, or if I cross-multiply, however you choose to think about it, we end up with 7 equals 0, and 7 does not equal 0. So it doesn't cross. I guess the only way I could possibly behave if I must be asymptotic, and if I must pass through this point, then it seems to me like I'll run along this, and then I'll go beep, and I'll come up to hit that, and then I'll go beep, and I'll go back down. And this is very poorly drawn, obviously, but this point here should be sort of a local max, okay? Let me just go graph this thing, and I'll bring you a better looking graph from Desmos. Hey, you know who else could graph this in Desmos to get a better look at it? You could do that. But sure, I'll do it for you. See you in a minute. Okay, got it. Got the graph. And it looks just the way I said it would. It's just kind of a line with a bump up. And if we put it on our grid, it would be pretty skinny. It would just look like this, roughly, very roughly. But there you go. It would be asymptotic, passing through that point. I can't get this right. All right, I don't care. You guys get the idea, I hope. But that's it. You would get that. No holes, doesn't cross the asymptote, but it's still kind of interesting because it didn't have any vertical asymptotes either, which is different. Let's do 13, which I did in class for one period at least. Period 3, they asked about it. Period 2, y'all might need to step your game up. You are not asking the best questions. What have I done now? I did something else. All right, let's do this one. It should feel really similar, except maybe more annoying. The difference between 12 and 13 is that 12, we were just a constant over a quadratic, so we knew that our horizontal asymptote was 0. This time, we're a cubic over a quadratic. So this time, we're expecting a slant asymptote instead of a horizontal asymptote. So we better begin by doing our polynomial long division. Well, really the way we should begin is by factoring. But factoring turns into a tricky situation because I would look at this cubic 4-termed polynomial and my heart would say, go ahead and factor by grouping. So I'd factor out an x to get an x and a 2x squared minus, I'd factor out an x squared, of course, dum-dum. So I'd get 2x minus 3. And then something horrible would happen because in the next set of terms, the only thing I can do is factor out a 1, and then I get 2x plus 1. And this means that factoring by grouping just is not the right strategy. It fails because I've got a term here or a factor and another factor, and they're not the same. Factoring by grouping only works when these two terms equal each other when you're done, and they don't. So factoring by grouping does not work in this problem. So I'm honestly not totally sure what the best approach would be, but I think we just forge ahead. I would just forge ahead with the long division. And it looks like this will be a long one. This is going to go in 2x times, giving me 2x cubed. Then notice we are missing a term in the middle. So we're going to get a 2x now, but there was no quadratic term. So if you want to put a 0 in there, that's not a bad idea. We're subtracting, that's plus. This cancels, I get negative 3x squared. We're subtracting, so that cancels 2. I drop the plus 1. We do it all again, and x squared goes into negative 3x squared, just negative 3 times, giving me negative 3x squared minus 3. Yeah, minus 3. And when we subtracted, there was no linear term, but you might want to plus 0x as a placeholder. When we distributed through, there was no x term, but you might want a 0x as a placeholder. But then we subtract to get our remainder. Oh, I'm probably off the screen because things have changed a little. Yeah. Make a little more room. Make a lot more room. Okay, so now when I subtract, to get my remainder, these cancel, these were irrelevant, and this is a 4. So a constant remainder is kind of irrelevant too anyway, but this means that I should get a slant asymptote that passes through negative 3 and has a slope of 2. So that's looking like the right slope to me. Oh, I can't move that? That's cool. Alright, bring that down to there. That's the right slope. Alright, do I have a vertical asymptote? I do not, because x squared plus 1 has no solutions. Does 2x cubed minus 3x squared plus 2x plus 1 have any zeros? I tried to talk about this to period 3. I don't know if they were listening. But but we are supposed to remember that polynomial functions like the one in the numerator, the only rational zeros, the only clean values of 0 that they have are the ones where you take the factors of the constant, which in this case would be 1 and -1, and that's it, and you divide that by the factors of the leading coefficient, which would be 1, -1, 2, and -2. And the only numbers, the only clean numbers at least, that stand a chance of making this function equal 0 are these combinations of things. So 1 over 1 is a positive 1, 1 over -1 is a -1, 1 over 2 is 1/2, and 1 over -2 is -1/2. And if I do all this same division with 1, the -1 over 1, I get all these same things. There are literally only 4 numbers, clean numbers, that could possibly be our zeros. And so what you could do is test them all. Plugging in 1 gives 2 times 1 minus 3 times 1 plus 2 times 1 plus 1, which is -1 plus 2 plus 1, which is 1 plus 1, which is 2. So xy, positive 1 is giving us positive 2. That's not a 0. Let's try -1. Plugging in -1 gives me 2 times -1 cubed, minus 3 times -1, so 1, plus 2 times -1 plus 1. So that's -2, take away 3, take away 2 plus 1. That's not feeling like it's going to work because that's -1, 2, 3, 4, 5, 6, 7 plus 1 is -6. So -1 is giving -6. That's not a 0. So how's about a half? Okay, let's test this again. This is going to be 2 times 1/2 cubed is 1/8. I just don't care anymore. I don't care anymore. So let's just do what we did with the last one. Do you guys remember in the last one when we just found our y-intercept and used our end behavior, right? And we knew that the only shape we could possibly take was to follow the asymptote, bump up to hit the y-intercept, bump back down because we had to be asymptotic. The same approach is going to work here. Let's find our y-intercept. Plugging in 0 again gives 1 over 1. So we know that 0 gives 1. That's our y-intercept. And honestly, I don't really need any other points because I know that I don't cross my slant asymptote. Hey, why not? Oh, right, because I have a constant remainder. This function could be expressed as x squared plus 1 plus 4 over 2x minus 3. And so that remainder over divisor term, it has no zeros, so we don't cross, which means really the only behavior I could possibly take, since my graph must lie completely above, is I must be asymptotic, asymptotic, asymptotic. By the end, I should be asymptotic, asymptotic, asymptotic. So what happens in the middle? I guess I come along, and then I come up, 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 up to hit that point, but then I turn and come back down, 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 and I'm asymptotic. This is the only shot, really. And by the way, guess who our x-intercept would be? It would be that last option, that -1/2. Looks like it's our one. It looks like it's our one real valued x-intercept. By the way, if I'm cubic, then I guess there's one intercept that's real, and then 2 more that are imaginary. Okay, that's how that works. You learned that in Algebra 2. I hope you did. Anyway, that's our shape. It's just another graph with a bump in it, I guess. Moving on to 14. There's only 2 left. And 14 is looking a little more run-of-the-mill because suddenly we're back to just somebody with a regular old denominator. We clearly have a vertical asymptote at 4, or is it a whole? Geez, how could I tell? Well, you got 2 choices. You could factor, or you could just plug in -4. 2 times -4 squared plus 3 times -4 minus 20 is what? 16, 32, take away 12, take away 20. Ooh, that is 0. So guess what we just learned? We just learned that x plus 4 is a factor here, and it will cancel. And this guy's going to have a hole at -4. And it's not going to have any vertical asymptotes. So this graph just got a little more interesting. By the way, you don't have to do what I just did. You just have to factor. If this is factorable, which it probably is. But we know that to factor a function like this, I just like to do guess and check. So it's got to be a 2x with an x. Then I need factors of negative 40, not factors of 20. So the factors of negative 40 that give me 3 would not be 2 and 20. It wouldn't be 4 and 10. It would be, oops, just kidding, 5 and 8. And I want it to be positive. So 8 better be the positive factor and 5 better be the negative factor. By the way, 8 being even tells me to chuck a 4 in this position so that my outer factor is 8. And chuck a negative 5 right here. There, I'm factored. And lo and behold, I do have a common factor of x plus 4 that cancels. So I don't have to do a heck of a lot more work. I immediately know that my whole entire graph is just going to be the line 2x minus 5 with a hole at x equals negative 4. So it's not even really a rational function. I mean, it is, because there's a hole in it. But my graph is just going to look like the graph of the linear function 2x minus 5. So where's my hole going to be? Well, plugging in negative 4 gives me negative 8 minus 5, which is negative 13, which makes me annoyed because, again, I can't fit it. So why don't I just cheat? I need to go down an extra 3. Is that right? So why don't I just get a few extra bits of grid. Okay, looking good. Looking real good. Yeah, looks perfect. All right. Oh my God. Oh my God. Okay, good enough. All right, we're supposed to be counting by 2s, so 6, 8, you would be negative 10. You'd be 11. You'd be negative 12. Oh, you'd be 13 right at the bottom? I should have gone a little farther. Okay, I don't care. Suffice it to say, negative 4, negative 13 is our hole, so I could plot that hole. It would be exactly there, and I'll make it nice and big. And I also have to pass through at negative 5, so I'm totally done. I just connect the dots here. I know that from this hole, I got to come up and pass through that intercept. By the way, how's my x-intercept looking? Looks like 2.5. And it should be 2.5, because that would be the x-intercept of my numerator. Obviously, the other half continues down and out. And this would be our graph. It would just be a line with a hole in it. The hole would be located at negative 4, negative 13. So we could answer all these questions now. It would be a lot of nones. Moving on. Okay, 15. Ugh. This feels really anticlimactic, but 15 is going to be a lot like 12 and 13 because we've got another denominator that has no zeros. So I guess this will probably be another line with a bump in it. So how's this going to go? Saying a lot. For vertical asymptotes, we know we have none because the denominator has no zeros. None. For the same reason, we have no holes. None. Because my denominator has the greater degree, we have a horizontal asymptote at y equals 0. We do not have a slant asymptote. For x-intercepts, we do have an x-intercept because our numerator does have a 0. So we pass through the origin, which means for y-intercepts, we also pass through the origin. But that's it. Oh, this is a weird one. Oh, I don't like this anymore. Okay, well, this just got a little more interesting. It got more interesting because, let's use a dotted line, let's use blue. I think I just said that our horizontal asymptote is here at 0. But I'm pretty sure I also just said that we have an x-intercept at 0, 0. So that would imply that this particular graph crosses its own horizontal asymptote. So I guess I'm below, and then instead of having a little bump out to hit a min, I must like bump out and then come back up and achieve a max and then come back down. Or maybe I do the exact opposite of that. So how could I figure out which of those behaviors I have? Well, I'll run a test point. Let's test a value to the left and a value to the right. So to the left, let's test -2. To the right, let's test +3, just for variety's sake. But -2 is giving me a -2 over +4 plus 2, so 6, so -1/3. So if -2 is giving me -1/3, then I'll be there-ish. If 3 is giving me 3 over 9 plus 2 is 11, 3/11ths, that's still roughly a third. Which of course I knew. But at 3 would be at about a third again. So, okay, I guess the only possible way that this graph could behave is to be under, cruise along, but then start to dip down, come up through that point we found, crash through the end behavior asymptote up to the point we found, and then start coming down and down again. And I wonder if there's any way we could verify this. Oh, I have an idea. Be right back. Alright, so yeah, graphing it on Desmos, confirms. Notice it doesn't exactly look like the most asymptotic thing in the world, but I've only gone out to like -6 and 6 on the axis. If we went out even to 10 or 100, then you'll find that we certainly come really, really close to this asymptote. Notice that we're only going from like -1 to 1 here, so these little bumps are really pretty flat too. In our graph here, you can see how flat we are. Here, I tried to accentuate it a little bit. I could accentuate it even more by just stretching this out. But these little maxes are quite low. They're only at a third, right? We knew that. Well, a little lower than a third. But that's our shape, and I hope you sort of understand how we got there, and I hope you understand rational functions in general. And if you don't understand rational functions in general, then leave a comment. Tonight I'll be looking at these videos. I'll be looking for your comments. Not, I won't say anymore that you should just leave a comment saying thank you. Although you should. This has been 1 hour and 7 minutes and 8 seconds of my life. So saying thank you is not a bad idea, but you could also include a timestamp and say, hey, I didn't understand what you were saying at this point. Or you could include a timestamp and say, hey, do you have another example similar to this that I could try? And I could try to throw another practice problem at you, but I think maybe the best, you could email me, but honestly, I don't know if I'll be looking at email because I'll be grading papers. But if you throw a comment in, then I'll try to be monitoring the comments tonight, and I'll respond there. And then anyone who's in YouTube will see those comments and see those responses and hopefully learn. All right. This is the only homework I'm going to do. You guys have answer keys for the first 2 homeworks, but you're not going to get videos for them. I just don't have the time. But this, I hope, was helpful enough. Anyway, good studying. I'll see you tomorrow. Bye.